Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 9, which is in which we will continue with our previous class, previous lecture as well, that is on heterogeneity. We will take a numerical problem in this heterogeneity and anisotropy in aquifers, and let us consider, say for example, a stratified aquifer a numerical problem of a stratified aquifer of say thickness 12 meters. So, this total thickness is say 12 meters and it consists of 3 layers as shown here. And this is the flow direction. The flow is along the layers or stratifications or strata, and the bottom layer has, say this is the bottom layer, it has a K value of 30 meter per day, and it has a thickness of say 5 meters, and the middle layer, it has middle and top layers have permeability of say 20 meter per day. This top layer also has a permeability of 20 meter per day. No, I am sorry, top has let us consider, take it as say 45 meter per day. And are of equal thickness. So, obviously, here if we deduct this 5 meter thickness of the bottom layer from the total thickness of 12 meter. So, we are left with 7 meters, and that 7 meters is equally distributed between the top layer and the bottom layer, top layer and the middle layer. So, that is 3.5 meter is the middle layer, and so is the thickness of top layer, which is 3.5 meter. So, the now we know the, and the flow is along the stratifications or layers or strata, and for this let us say find out what will be the equivalent permeability as well as what will be the transmissivity. So, now let us come to the equivalent permeability. So, K E in this case is given by summation K I B I from 1 to n divided by summation B I. So, in this case we have to sum, there are 3 layers. So, there will be 3 terms in the numerator. So, that is 45 into 3.5 plus 20 into 3.5 plus 30 into 5. So, this is in the numerator, and in the denominator the total thickness, which is say 12 meters. So, this will be the equivalent permeability, and in this case, so this equivalent permeability K E will be simply that is 45 65 into 3.5. So, that is here I am computing here. So, this is 65 into 3 into 3.5 plus 150, which is 377.5 divided by 12, which is 31.46 meter per day. So, this is the equivalent permeability, and let us also determine the estimate the transmissivity, or it is also known as transmissibility. So, this is simply equal to K E into sigma B I, or which is simply equal to, this is summation 1 to n K I into B I. So, this is as will be the numerator of the one. So, this is 377.5 meter square per day. So, this is the value of transmissibility. So, here I was mentioning here. So, there were 3 layers, the top layer and mid layer having 3.5 meter thickness each, and bottom layer having 5 meter thickness, each with the hydraulic conductivity or coefficient of permeability of 45 meter per day, 20 meter per day and 30 meter per day respectively. So, in this case, and the flow is along the stratifications. So, in this case it is simple, we just apply the formula and get the equivalent permeability, which is a 31.46 meter per day, and the transmissivity for this entire aquifer consisting of 3 strata is 377.5 meter square per day. So, this is just an illustration of one simple numerical example consisting of an anisotropic aquifer, confined aquifer with 3 layers or 3 stratifications and flow along the one. So, now let us come to the groundwater flow rates and flow directions. Of course, so this groundwater we have been abbreviating as GW. So, we know that by Darcy's expression, the groundwater flow velocity is given by the hydraulic conductivity K into I, and here and the groundwater flow rate obviously is given by the velocity into the area of flow, which is K into I into A. So, accordingly, if we can estimate all these 3 parameters, the hydraulic conductivity K, the hydraulic gradient I, and the area of cross sectional area of flow for the groundwater. So, if we estimate each of these parameters, then the product of these three estimated parameters will give us the estimated groundwater flow rate. Now, let us consider, say for example, a stream or a river which is flowing above an alluvium, something like this, and here let us say this is the water table, and this is the stream. Let us say this so this is the alluvium, which is essentially an aquifer, and say let us say the width of this alluvium is something of the order of say 1000 meters, and the average depth of this alluvium, so this is the average width and the average depth, say that is say of the order of say something like say 50 meters. Then in that case our cross sectional area A will be 1000 into 50, which is 50,000 meter square, and if we multiply this by the groundwater flow velocity given by the Darcy's law, which is K into I, and suppose the hydraulic gradient is say the hydraulic gradient is say 10 meters or say maybe 5 meters, say let us take this to be 8 meter in 1000 meter length. So, this will be 8 divided by 1000, which is 0.008, and obviously that is the hydraulic gradient, and then the coefficient of permeability, if we take this as say something like say 100 meter per day, then in that case simply these are the estimations. Permeability or hydraulic conductivity is estimated as 100 meter per day, and the hydraulic gradient is estimated as 0.008, and the area, again this is also an estimation only, that is why I am using this approximately equal to sign, because this is based on average width and then average depth. So, in that case, so now we can write down this Q is equal to 100 into 0.008 into 50,000. So, this will be 50,000 into 0.8. So, this is of the order of say 40,000 meter cube per day. So, this is our estimated value of groundwater flow. This is just to give an idea. So, basically here we need to estimate each of the three parameters. The first one is this the area of cross section of flow, area of flow cross section for the groundwater. The second one is the hydraulic conductivity K, and the third one is the hydraulic gradient I. So, these estimates should be as realistic as possible, and based on that, once we estimate each of these 3 parameters, then simply take the product of this. So, that will give us the estimation. So, that is why let me use the approximate equal to sign here. So, this alluvium with say these dimensions, average depth of 50 meters and average width of 1000 meters, which is essentially the aquifer below the stream. So, will yield a groundwater of approximately 40,000 meter cube per day, when the estimated hydraulic conductivity is 100 meter per day through this the material of this aquifer or alluvium constituting this aquifer or alluvium, as well as the hydraulic gradient, which is estimated as 8 meter in 1000 meters length along the flow. So, this is just on to give one idea of this estimating the groundwater flow rates. Now, let us come to this groundwater flow directions. So, here so we need to go by what is known as the flow net, which is essentially a network consisting of 2 sets of orthogonal lines, the stream lines shown by the green color this one, and the equipotential lines. Let me show them by the so these are the equipotential lines. And these are the stream lines or the flow lines. Also known as flow lines. Now, let us consider the stream wise, let us partition this flow net into square grades, and say let us say the total flow between 2 neighboring streamlines, this be dq, and here also this is the flow is dq between the bottom and the middle streamline, as well as the middle and the top streamline. And let us write down the head values or the total hydraulic head values along each of the equipotential line. So, let this be H here, and obviously due to friction and other losses there will be a continuous head loss. So, for the along the next equipotential line, let the head be H minus dH, and in this case it can be H minus 2 dH. Okay. So, now and also let us consider this stream wise length as ds and let us consider the length, that is the ds is the distance between 2 adjacent equipotential lines, which is by along the stream wise, that is why it is denoted by ds, and this the perpendicular or the meridional. So, which represents the distance between 2 neighboring streamlines, let this be dm. Okay. So, now we know that by the definition of this hydraulic gradient. So, this is dH by ds, basically the change in the head per unit displacement along the streamlines. Therefore, here if we consider unit width perpendicular to the paper. So, therefore, this total discharge Q is simply given by the hydraulic conductivity K into the hydraulic gradient dH by ds. So, this is the velocity multiplied by the area. So, this is simply given by 1 into dm. So, this is the area. Okay. So, therefore, this the groundwater flow rate, and here because since the grid is almost a square grid, so we can say this ds is approximately equal to dm, that is a stream wise distance is approximately equal to the perpendicular distance along the flow net. So, therefore, we can write down the expression for Q is K into dH, and suppose this dH, the total head H which is there in the along the upstream most equipotential line, if this is and along the downstream most point, if the head be 0, it is the entire head is lost due to friction and other losses in say n along n such equipotential lines. So, in that case, so this dH can be approximated as h by n, where n is the number of segments of equipotential lines. Therefore, Q, which is the flow per unit width, this is a flow rate per unit width, is given by K into h by n, and the total flow rate, for this we have to if the flow is divided into m channels, m channels, m number of channels in the streamwise direction, by streamlines, then total flow, so that is Q is equal to m into small q, which is simply equal to m into K h by n. So, this is the expression for the total flow rate. So, here m is the number of channels along the streamwise direction, and K is the hydraulic conductivity, H is the total head in the upstreammost along the upstreammost equipotential line, N is the number of segments in the along the off equipotential lines. So, in that case the total flow is simply given by this M K into H divided by N. So, this is how we can estimate the total flow, and also we can estimate, say, using the direction. So, we can estimate the groundwater flow direction also. So, like this we can estimate the flow rate as well as the flow direction. Now, let us consider an anisotropic case wherein, say, consider an anisotropic aquifer. So, here which has a in the xz plane with hydraulic conductivities Kx and Kz along x and z directions, and typically in case of the alluvium or aquifers, so this Kx will be greater than Kz. So, the equivalent hydraulic conductivity so this is Ke can be approximated as the square root of the product, that is Kx Kz. And say in such case, because of this anisotropy which results in different values of the parameters, the groundwater flow parameters such as hydraulic conductivity and other parameters like transmissivity and so on, the aquifer thickness, either the geometric parameters or kinematic parameters. So, what happens is we need to estimate the flow rate through such such anisotropic aquifers by estimating the equivalent hydraulic conductivity, and in such case the flow lines, that is the streamlines, will not be fully perpendicular to the equipotential lines because of anisotropy, and in such case if we transform this into an isotropic condition, equivalent isotropic condition, in that case only the flow lines will be perpendicular to equipotential lines. So, here let us say the flow net analysis of for an earth dam, let us consider, say for example, this is the and in this case suppose these are the flow lines and the equipotential lines, because of anisotropy they will not be intersecting orthogonally, and in this case, so if this is the total length L, so here let me write this as this is a true anisotropic section with say Kx is equal to 9 Kz. So, this is the downstream one, and this is the xz plane. This is the x direction and then this is the z direction. So, this is figure A, which represents the true anisotropic section with say Kx approximately equal to 9 times Kz. Then, so this can be transformed into an equivalent transformed isotropic section. For transforming this into so this is B is the transformed isotropic section. So, in this case, so this length, the length L will be, so this is L dash. So, this L dash will be equal to L into under square root Kz by Kx. In this case, this will be L into under square root Kz by 9 Kz. So, this L dash is simply equal to L by 3. So, this L dash is L by 3, and in such case, for this transformed isotropic section, in this case, so this distance will be m, whereas in this case this distance of a grid, so that will be 3m. So, it is only in case of this, because of this anisotropy, the streamlines as well as equipotential lines, they will not be perpendicular to each other, they will have some this one, and only in case of a transformed isotropic section. So, it will have a transformed length which is given by, that is L dash will be equal to L by 3 in this case, and similarly in this case, since suppose we are taking this Kx is approximately equal to 9 times Kz. So, therefore, here we can say this Ke is approximately equal to 9 Kz into Kz, which is 9 Kz square under square root. So, this is 3 Kz. So, this is the equivalent is equal to Ke. So, therefore, so for this anisotropic aquifer with varying hydraulic conductivity values along x and z directions. So, the equivalent hydraulic conductivity is given by 3 times the hydraulic conductivity along z direction, and the base width of the the transformed isotropic section through which the flow groundwater flow takes place will be given by L by 3, and so this is corresponding to the expression this L dash is equal to L into under square root kz by kx. So, like this the and say let us consider another case wherein there is a weir or a barrage with say some kind of upstream head, and of course weir or a barrage. So, let us consider this to be almost impervious, and in this case say suppose let us consider this as the channel, and in this case what happens is the channel is pervious, whereas this is impervious dike or barrage or weir. So, in this case the streamlines will be and let us consider this also to be the so this is the impervious sheet pile. So, in such a case the streamlines will take the shape if the downstream water level so in this case the streamlines will be having streamlines of the flow lines so these are the flow lines, and we can construct the so if this is the head difference between the upstream and downstream. So, if we divide this head difference into, so in this case there are 1, 2, 3, 4, 5, 6, 7 streamlines are there, and if we divide this into say 7, it is let us I am sorry, that is this is not the downstream, this one. So, this is the downstream water level, and if we so this difference between the upstream water level and the downstream water level, if we divide this into 7 divisions, so here we get our so this will be the downstream most equipotential line, then followed by the next equipotential line will be like this, the third equipotential line like this, and the fourth equipotential line, and the fifth equipotential line, the next equipotential line, so to get to know the flow direction at any particular location, we need to use the concept of flow net, and we need to construct the flow net. So, therefore, the streamline or the flow line at any particular location will give the groundwater flow direction at that particular location. Okay. And so, this is regarding the now let us go to the general flow equations through porous media. So, here, so let us consider a two-dimensional flow initially, and again later on let us extend it into a three-dimensional flow domain. So, in this case, this is the flow domain, two-dimensional flow domain, and then so these are the streamlines shown by this green color, and let, considering the unit width, let the flow across this boundary of the square flow domain be q x I. So, I standing for inlet section, and similarly the flow here per unit width, let this be q x comma O, and then similarly along the bottom boundary. So, let the flow be q y comma I, and then so this is the inlet, and then so here let this be q y comma O, and let the dimensions, let since we are considering this to be a square grid. So, let us assume the dimensions of each side of this flow domain as W. Okay. And in this case, we know that the Darcy's expression holds good, that is the groundwater flow velocity is given by minus k into d, the partial derivative of h with respect to s. This h is the head and s represents the displacement along the flow line or streamline. Now, let us consider, let this for this flow domain, let T x comma T y be the transmissivities. In x and y direction. Okay. So, therefore, this qxi, we can write this as qxi can be written as minus Tx, which is the transmissivity or transmissibility in the x direction, into the width of the flow domain, that is W, and we are considering unit thickness. So, the area will be W into 1 into dH by dx in the I direction. Similarly, Qx, the outflow through the right boundary, which is denoted by Qxo, is given by minus Tx, which is transmissivity along the x direction, into W into dH by dx at this outlet section. Okay. Now, let us take down the change in the flow rate along x direction and y direction. So, similarly, here we can also write down the expressions for qyi and qyo. Let me write here. So, this is qyi can be written as minus ty into w into dH by dyi, and so qyo is equal to minus ty w dH by dyo. So, therefore, the total change in flow rate along x and x direction and y direction. So, this is basically, this is essentially, that is the flow rate. So, this is simply given by qxi minus qxo. So, this is the change in the flow rate along the x direction plus qyi minus qyo, and this must be equal to, this can be expressed in terms of the storage coefficient S multiplied by the area. In this case, this will be W square, this will be the cross sectional one, and multiplied by the rate of change of h with time, the partial derivative of h with time. So, therefore, so we can write down the minus Tx into dH by dxi minus dH by dxo let us divide the whole thing. This is Tx into W minus Ty into W dH by dy I minus dH by dy O. This must be equal to minus S into W square into dH by dt. Okay. So, we can write down we can simplify this as Tx into dH by dx I minus dH by dx O divided by W minus Ty into dH by dy I minus dH by dy O divided by W. So, this is equal to minus S into dH by dt. So, here in this when this W is extremely small or infinitesimally small, in this case, so this the term under the square brackets can be approximated as the second partial derivative of h with respect to x and second partial derivative of h with respect to y. So, therefore, so the terms in the square bracket can be approximated as second partial derivatives of h with respect to x and y. So, therefore, suppose if we call this as equation 1. So, this equation 1 becomes Tx into d square h by dx square plus Ty into d square h by dy square. This is equal to the storativity S into dH by dt. Okay. And this Tx and Ty, so we can be simplified as Kx into W, Kx into say B, which is the Bx, you can say B into d square h by dx square plus this Ty can be substituted as Ky into B, where B is the saturated aquifer thickness, into d square h by dy square. This is equal to S into dH by dt. Or the same this. So, therefore, if this is equation 2 and then this is equation 2 and then this is equation 3. So, equation 2 can be simplified as d square h by dx square plus d square h by dy square, which is equal to s by t into dh by dt. So, this equation 2 here, this is for an isotropic aquifer. So, in this case, this is T is equal to say Tx is equal to Ty. Okay. So, this is the basic groundwater flow equation in the 2 dimensions, and of course, if we add the 3rd dimension also. So, in that case, so this is the basic 2D groundwater flow equation. So, in the next lecture, we will discuss, we will extend this this 2-dimensional groundwater flow equation to 3-dimensional one, and also we will see its variation in when the flow is steady and this one. Thank you.